Today we're going to do a quick review of things that we have learned, not of everything, of course, in the last 7 lectures. I start with the last lecture. We had these quantum numbers, and they describe the energy, the shape, and the spatial orientation of electronic orbitals in an atom. Okay? So how many quantum numbers do we have so far? 3 so far, okay? There's a total of 4, but you don't know the 4th one yet, okay? So, so we had the principal quantum number, n equals 1, 2, and 3. What does this principal quantum number give me? The energy. It gives me the energy level. So if I have quantum number 1 or quantum number 3, which one is the higher energy? Okay, it's a negative, but negative smaller, so that's the higher energy, okay? And now we talked about our orbitals. We know also that the total number of nodes, what kind of nodes do we have? What is a node in an orbital? The wave function goes through 0, okay? You won't be able to find an electron at all there because it goes through 0. The probability is absolutely 0 to find that electron. So what kind of nodes are there? Radial, or spherical, and angular nodes, yeah? Okay? So the total number of nodes is n minus 1. So if you have n equals 1, how many nodes can you have? 0, okay? So if you have n equals 1, the angular momentum, this is the second quantum number, it gives you the shape of the orbital. The shape of the orbital can be L equals 0. That means L equals 1, L equals 2. It cannot be more than n minus 1. So if n equals 1, n minus 1 is 0, so you have only this L equals 0, and with this you have an s orbital. If L equals 2, that can only happen if n is 2 or larger. N equals 2, then you can have either an s or a p orbital because you have 0 and 1, okay? If n equals 3, how many different types of orbitals can you have? 3 different types of orbital, types, not how many of each orbital, the types of orbital. So n equals 3, you can have L equals 0, 1, 2. N minus 1 is 2. So this can be an s, a p, or a d orbital. And so far, if they're in the same quantum number, if it's a, so we have, how high has n to be that we have a d orbital? The first d orbital starts at n equals 3, okay? So that would be a 3d orbital, all right? The 3d orbital. So if you have a 1s orbital and a 2s orbital, which one has the higher energy? The 2s. You have a 1s orbital and a 3d orbital. Which one has the higher energy? Okay. You have a 3d orbital and a 4f orbital. Which one has the higher energy? Okay, there we go. Good. So the number of angular nodes is L itself. So if the total number of nodes is n equals 1, so in the first quantum number, then you have total nodes is 0. So it's, how you call it, spherical, it's radial symmetric, yeah? If you have n equals 2, you have the total number of nodes is n minus 1, is 1 node. So what can be L? L can be 0 and can be 1, okay? So if L equals 0, what is that node? What is that node? L is the number of angular nodes. It's a radial node then, because the total number is n minus 1. So of course, you have n equals 2, that's a 2s. So it has how many nodes? 1. Now you have it n equals 3 and L equals 0. How many nodes you have? 2. What are they? Radial or angular? Radial. Think of it, of the s orbitals as an onion. The higher you go, you have one more layer of skin, and in between is the node where the skins touch each other. There are the nodes. You can look at this in this way. Now, let's see, if we have a n equals 3, and we have a 3s orbital, how many nodes do we have? 2 nodes. Are they angular or radial? Radial, okay. But you can also have, if n equals 3, you can have p orbital, okay. So the number of total nodes is n minus 1. So n minus 1 is 2. So how many nodes can you have here for a 3p orbital? 2. And how many angular nodes you have? Yes? How many angular nodes you have? 3p orbital. Yeah, and how many radial nodes you have? No, 1. Okay? If n equals 3, yeah? And so the total nodes is n minus 1. All right? So we have 2 nodes total. Now you have the number of nodes. We see the p orbital here. How many angular nodes can it have? 1 angular node. I showed you that picture. I cut through it, and there were 2 radial. There was a radial node, and there were an angular node in the middle. Yeah? I didn't point this out very well to you. That's why I'm doing it now. So it only can have 1 angular node, and since you have n minus 1, it's 3 minus 1 is 2. So you have 2 total nodes. You have 1 angular and 1 radial or spherical node. Okay? Good. That's important. So now we come to the magnetic quantum number, the third quantum number. So we have defined S, P, D, and F. What would be that? Would be N would be 4, N would be 4, okay? Then L would be 3, okay? Now how many angular nodes would you have in an F orbital? No, the L. If L equals F orbital, 3. How many angular nodes? 3. How many radial nodes? N is 4, minus 1 is 3. The total number of nodes is 3. And so how many angular nodes do we have already? 3. So you have no radial nodes. Okay? All right, this is in your homework. This is done very well, actually. So the magnetic quantum number can be go from minus L to minus L to minus 1 to 0, L minus 1 to L. That means it gives you the orientation in space, okay? So if you have an S orbital, what is L? 0, no orientation. If you have a P orbital, what's the orientation? That means how many orbitals do you have? 3, okay, that's correct, X, Y, and Z. Now D orbitals, how many, what's the L range? Minus 2, minus 1, 0, plus 1, 2. Okay, plus 2. So this is 5 orbitals. These are 5 orbitals. So you have 5 different orbitals for the D. And you go to the F one. F would be n equals 4. L would be 3. And with this m sub L would be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. How many are those? 7, okay? Good. So that gives you the orientation. I have given you here this again. So at this point, we understand. Our understanding at this point, it's not totally correct, but at this point our understanding is if n equals 1 or n equals 2, the orbitals that are in energy level 2 have different shapes, but so far they have still the same energy. The energy would be this here, n equals 2. You know how to calculate this? This is the Bohr's, what they call it, the Bohr's equation or something, yeah? And we come to that. You probably had this in your book. I just say, but is E equals minus z square divided 1 over n square times the Rydberg constant, yeah? Good. So if you have a n equals 4, so the E of 4, the energy of 4, how many orbitals do you have in total that have that same energy at this point? You have how many? So you have 7 and 5, okay? This is 12, and then you have 3 is 15, and you have 1 more. You have 16 orbitals. They are different, okay? Because they either have different orientation or different shape, and so 16 orbitals in level 4. Yeah? Okay. Now I show you here again, that's the 3s. How many radial nodes? 2 n minus 1, so that's 2 in this, and L equals what? L equals what? 0. Why? Because it's s orbital. So now you should be able to answer this even more educated than the last time. I give you exactly 1 minute. It's just to show that you were here. Which has the most radial nodes, the 4f, the 3d, or the 4s? Let's do that then. 1 minute. Don't forget to click in. You should really know this now. We also put you an orbital viewer on B-Space. You can go and click on the tab. There's an orbital viewer. Play with it. Does all kinds of interesting things. Yes, there we go. Excellent. Would be sad if it would be different. So what is 4f? 4f, what's the number of total nodes? N minus 1, n is 4, n minus 1 is 3. Total nodes is 3, okay? What's the quantum number for f? 0 is s, 1 is p, 2 is d, and 3 is f, okay? 3. So how many nodes did we say we have? 3. So that must be 3 what kind of nodes? Angular nodes, all right. Let's talk about the 3d. We did this just, okay? D is, what is the, so n is 3. What's the number of total nodes? 2, all right? So what's L? L goes from what? L would be 1. S, P, D. It's not 1, okay? 0, 1, 2. 0 is S, P is 1, D is 2, yeah? So this is 3. L is 3. That's the number also of your angular nodes. And how many have we total? 0 radial nodes, okay? 3D, let's do this again. Total number of nodes? 2. 0 is S, 1 is P, 2 is D. So you have 2, how many angular nodes you have? 2. How many total nodes? 2. Good, you got it. 2 total nodes, no radial nodes, okay? All right. 4S. L is what? 0. Total number of nodes is what? 3. Total number of radial nodes? Total number of angular nodes? Y. L is 0. Okay? All right, good. So that was the answer here, and with this 4S that this has 3, we have proven that. Yeah. So there I show you some more projections here. And these are, for example, the 3D electrons, and these are the 4F. So you should be able to recognize them, pictorially recognize them. Just by seeing how many nodes there are in there, you can see that. So we've seen already that the angular momentum quantum number L also stands for S, P, D, F. We have done this now quite a bit. The orbitals can have radial or angular nodes. We just practiced this, i.e. spatial locations where the wave function intensity goes through 0. And the wave function intensity goes through 0, the electron has no possibility being there at all. There's no probability for the electron to be there. So let's go to lecture 1 topics. We had lecture 1 where we blew up these balloons. We had hydrogen. and oxygen react to water, and you needed to have the right ratio, the stoichiometric ratio, to completely react that the hydrogen with the water. So you needed 2 parts of hydrogen and 1 part of oxygen. In this case, we could volumes, actually, it was very easy to do. We get 2 parts of water. Now you know we need 2 moles of hydrogen, 1 mole of oxygen gives 2 moles of water, all right? So the chemical reactions have to occur in stoichiometric ratios. So now you can read these things. This is an energy diagram. This was the energy of the reactants is high or higher than the energy of the products. It had to go through an activation barrier here. That's a transition state, but we needed to put a little bit of energy there, and then we got the reaction started, and the energy that was released in the reaction then got the other parts of the reaction started. So is the other products in a lower energy state than the reactants? Yes, the product, this is the energy, 0 would be here. The reactants have a higher energy state than the products. You've heard it all, you've seen it. The energy was released. Hydrogen and oxygen formed water and gave energy, okay? So that's an exo or endothermic reaction? Exothermic reaction. So how do we convert between numbers of moles and numbers of atoms? So we want to have something to weigh because we can't count the atoms. So we relate the atoms, they react on a molecular scale, as we have seen with our stoichiometric equation. But how do we relate this now? We can't count the individual molecules out. We need to weigh something and need to weigh or take a volume of hydrogen and a volume of oxygen, and this has to be in the right ratio. So how do we do that? So we need to connect the macroscopic matter to the microscopic, to the atoms and molecules. And we do this using Avogadro's number. Avogadro's number is a very large number. It's 6 times 022 times 10 to the 23rd. It's a huge number, as we have learned. And this is just a number. You can have Avogadro's number of people. Hopefully, we will never get there, okay? Can have Avogadro's number of stars, okay? Or you can have Avogadro's number of atoms or molecules. That would be more likely. So we call this, if we have 12 grams of carbon-12, the isotope carbon-12 has exactly this number of moles. Of atoms, I'm sorry, of atoms. And so 6.022 of molecules or atoms we call a mole. That's our new secret word, the mole, all right? You can also write it without the E, but I like it this way especially because it refers to the animal or to the spy, you never know. And so we also have seen that the molar mass is given in grams per mole. See, now I write it how it's really written. As we said, carbon-12 is exactly 12 atomic mass units, and we say this AMU or U, it depends where you read it. And all the masses of the other atoms, or the masses of all other atoms, are given relative to the standard. So we need to know 1 mole, if it's twice as heavy, it has twice the molecular mass, all right? Twice the molecular mass of carbon-12 would be something with 24. I know the light's not working. Where is 24? You can see it. Magnesium, right there. There's magnesium. Thank you very much. It's magnesium. All right, I actually couldn't read it. So that's why I have you, okay? The atomic masses are averages of the isotopic masses, and we talk about isotopes in a minute, because you can have different number of protons in the same atom. Not in the same atom, in the same element. And then you call it an isotope. But since protons and neutrons have about the same mass, so it's heavier. And the relationship between AMU and grams, we already said this, is 6.022 times 10 to the 23 atoms times 12 AMU per atom is 12 grams. So with this, this would be 1 gram, and 1 AMU, and this is what I'm pointing at, is 10 to minus 27 kilograms. It's a very small number. That's why we call it an AMU, a U. You don't want to write always 1.66 times 10 to the minus 27 kilograms. All right? So, lecture 2 topics. We have talked the structure and the size of the nucleus and the atom. So we know that the nucleus is positively charged. Why is it positively charged? The protons have a positive charge. And what else do we have in the nucleus? Neutrons. They are neutral. They make the protons and the neutrons make the most of the mass of an atom or an element. Because the electrons are much, much lighter, by 1,000th about lighter than a proton or a neutron. Okay? So you need to have 1,000 electrons about to get the mass of one neutron. So we don't have 1,000 electrons. No. So the protons gives the charge. All the mass is in the nucleus. Most of the mass, no, all the mass we can actually say is in the nucleus. And the proton number gives you what? The element number. It is specific, the number of protons. If you have 6 protons, what is it? Carbon. If you have 92 protons, what is it? Uranium. Okay? So you write this here. If you have an equation or if you want to write a symbol of nuclei, you can write this like this. You put here the proton number, and then you have the atomic mass number is the number of protons plus the number of neutrons. And this is the number. What was that? Where did it go? Okay, that's great. Actually, it works fine on my computer. I tested it because this morning it did something differently. Okay, so what should be here? The number of protons plus. There it is. I was so fast that I went 5 steps. So let's see what it says up there. No, I don't want to stop iClicker. Aha, something, neutrons, okay? Neutrons. The Z plus N neutrons gives A, okay? You will remember this now because we had this mishap here. So now I have to go back here. No, I don't want this at all. So now I want it. So we combusted some hydrocarbon. I think it was very warm in the back of the room there when we combusted this, okay? So it reacted with oxygen to form CO2 and water, isn't it right? CO2 and water. And then we said, we want to know what that hydrocarbon was, and with this, we use a mass spectrometer. And the mass spectrometer sorts us masses, but it only gives us relative masses to each other, all right? So we would have combusted this hydrocarbon, and we would have collected it and put it in our mass spectrometer, and we would have seen then that we get some signal, a signal of carbon dioxide and of water, for example. Now let me explain again how this mass spectrometer works. You put in your compound and you strip off electrons. You do this. That means you ionize. If you if you strip off electrons, then you ionize it. And if you have an ionized atom, what is it then? An ion, okay? And ion is, how is it charged? Positive. Because you're missing electrons. So now you can accelerate it. You attract it with a negative charge, and now you accelerate it, and then you put it through a magnet. And charged particles are deflected in a magnet, or in a magnetic field. And the faster they move, the more deflected they are. That means kinetic energy is 1/2 mv squared. So if they are small, then they move, let's put it this way, okay? So they are this is the lighter particle, it's more deflected. Now we use the heavier particle, it's less deflected, okay? And if you look at this here now, at the end, we sort them like in a bin. And this bin can be a detector. And then we go in the bin and we calculate, we pull out how many do we have of this mass and how many do we have of that mass. If we have double the amount in this bin than in that bin, so you have a ratio of 1 to 2. So that would be the intensity, how many you have in each bin. And the bin gives you the mass itself. So this is what a mass spectrum does. And you look at this mass spectrum here, it only goes from 0 to 50 mass units, but you could go further, much further. And actually a real mass spectrometer that can be billions of a mass it can separate, yeah? Not just whole masses. But for you to understand the difference here is, so what we have mass 1, what could that be? Hydrogen. And mass 2, what could that be? A hydrogen molecule. Or deuterium, heavy hydrogen. So heavy hydrogen, how many neutrons does it have? Okay, let's do that again. Hydrogen, how many neutrons does it have? Huh? 0, okay. So heavy hydrogen, how many neutrons does it have? 1. How many nucleons does heavy hydrogen have? Nucleons, protons plus neutrons, A. Okay. How many? 2, exactly. All right. So what could be 3? Could be all kinds of stuff. Could be a heavy hydrogen and a regular hydrogen, all right? Or a helium-3. Now we have 12. What could that be? That's our standard. Carbon-12. The height of the line tells you how many you have there. I said that. If you have in this bin 1, in this bin 5, so it would be a ratio of 1 to 5. So you have 5 times more here, but it's still the same mass. The height of the line gives you the amount, the intensity. Yeah? It's like the same with photons. If you throw more photons in the same wavelengths at something, it's not going to change the energy, but it changes the intensity. It will be brighter, but the same wavelengths. Okay? So then 13, we just drawn it, the line has nothing to do with the line that we can put in the labeling. You know, otherwise I can put in the labeling. Okay, so what would be 16? That's like a common thing. Oxygen 16 and 18? Water. Water and oxygen 18. There we go. And if we would have something here 20, what could that be? Water, heavy, not heavy water. Heavy water would be the hydrogen would be heavy. That's what we call heavy water. But it's a good idea. Heavy oxygen water, all right? So that would be H2O, oxygen 18, okay? So then we have 32. That would be oxygen, the oxygen molecule, or the oxygen 16-18 molecule would be 34. And 36, what would be an oxygen 18 molecule, just to give you examples, all right? Carbon dioxide. Carbon is 12. Oxygen is 16 times 2 is 32 plus 12 is what? 44. There we go. Carbon dioxide, regular carbon dioxide. Now I could also have carbon dioxide with carbon 13, so mass unit would be 1 more, it would be 45. So let me ask you a question. In nature, of course, the ratio of oxygen 16 to oxygen 18 is not equimolar. But let's just assume for the heck of it that we have same amount of oxygen 16 and same amount of oxygen 18, all right? And we run this through our mass spectrometer, all right? And now there was my oxygen 18, same number of oxygen 16 and same number of oxygen 18. Of course, they react. The oxygen doesn't stay around by itself, okay? So I get this spectra with mass 32, 34, and 36, And this is a ratio of 1 to 1 to 1. This is a ratio of 1 to 2 to 1. This is a ratio of 2 to 1 to 2. So this here is half as high as here, or this here is double as high than that one. Okay? So what is the answer? Which is the correct oxygen 2 spectrum? B, okay, you remember, and you know now. So you have for those who haven't gotten it yet, you have the same amount of oxygen 18 or oxygen 16. White and red billiard balls in a sack, large number, okay? You take out a white one. Do we have the same probability to pick a red or a white one from here? Yes. So you can have a red one and a white one, okay? So now if you have a white and white, you have oxygen 16, and the white and red is oxygen 16, oxygen 18. Now you take the red one. You have the same probability picking red and white. So oxygen 18, 16 is white, red and white. Oxygen 18, 18 is red and red. So what is the ratio from oxygen 16 to oxygen 16, 18 to oxygen 18? 1 to 2 to 1. And what was that? That was this number here. No. Yeah, okay, even better. 1 to 2, that's what I just showed you here. So this is, now you do the reverse, and you get this one here. So we have 2, 1 to 2 to 1. You see that? Who asked me what the length is here? See that? Look at these things here now. Yeah, we have it nicely animated. Now we're going to get this one here. And now we're going to get this one. There you go. This came from up there, didn't it? You asked me about it. So 1 to 2 to 1. So that was the number, B was the answer. Now, but this is not enough. We have now combusted, and I'm switching between oxygen and our hydrocarbon. It really doesn't matter. So we have combusted our hydrocarbon, and what do we get is a ratio. This ratio does not necessarily tell me the exact molecular formula. It tells me the distribution, the ratio of atoms of one sort and another sort in that molecule. But I don't know how many of each you have. I know the ratio. So if I have, for example, methane would have a C is 1 to 4 ratio, 1 to 4 carbon to hydrogen. Ethylene would have a carbon to hydrogen of 1 to 2. Acetylene would have a carbon to hydrogen of 1 to 1. But I know these are not the formulas for the molecular formulas. So how would you get the molecular formula? No, you take it before you combust it, put it through a mass spectrometer, and then you know what the ratio was. Okay? Exactly. You can weigh it, and then you can relate it. So that would be then here the CH4. That's, in this case, the empirical is also the molecular formula, but in this case, that's the empirical formula, the lowest or the smallest whole number ratio, but the molecular formula is C2H4. Acetylene, the molecular formula is C2H2, all right? So you need to know the difference between empirical and molecular formula. Let's see what is, yeah, I gave you that. So lecture 4 topics. So we have seen light can be electromagnetic radiation. We know that. It's a wave. It travels with the speed of light. And the speed of light is 3 times 10 to the 8 meter per second. And it has a wavelength, lambda. That's from crest to crest is the wavelength, one full wavelength. Now, the wavelength is lambda, and the frequency is nu. And nu is related to lambda, is nu equals c divided by lambda. Or lambda times nu is c, or you can ever how you want this. Or lambda is c divided by nu, all right? That means the frequency and the wavelengths are inversely proportional to each other. So you have a wavelength E of lambda is 700, and the wavelength of lambda is 400. This is the range of our visual spectrum about. So which one has more energy? 400. The higher the frequency, the shorter the wavelength. E equals h times nu. You know that now already. So we have seen light can behave as a particle. But we have done this experiment just to show that you get, when you have waves, with any kind of waves, when they interfere with each other, you get an interference pattern. It looks like this. And the shape of that pattern, or the spacing of the interference lines, is depending on the wavelengths. So what did we do? This was, what kind of light did we have to use? Polychromatic or monochromatic light? Monochromatic, one wavelength, all right? So we have here the interference of monochromatic, up, down, up, down, up, down, up, down, up, down, up, up, down, up, down, up, down, up, down, up, down, up, down, up. So you have what? A constructive interference. That means they add to each other, the amplitudes, and you get a high probability to find that photon here, that light. Now, if you go here, to this point, which wavelength has to travel, which wave has to travel longer? The wavelength is the same. This wave or this wave? Okay, this wave here has to travel longer. Now, if I have a longer wavelength, compared I have this one wavelength that made that pattern, if I have a longer wavelength, where would it meet? Would I meet earlier here, or would I meet further out here? Further out. And if I have a shorter wavelength, I meet earlier, okay? Because the point has to be that you have to have constructive interference. And so it has to travel a whole wavelength longer, this one, than that one, in order to come to here, to this point. All right? And if it's longer, it has to travel further. All righty? Good. So we have continuous absorption. You can see that there's an absorption of light. If you don't use a grating in your absorption spectrometer, it doesn't have a grating. So you just check the intensity before and after it went through something and it absorbed that light, and then you get a continuous spectrum. It looks continuous. Really, it's not continuous, but it looks to us because we haven't dissected it. It's a cheap instrument. It's not a line spectrum. So that looks like this. I say, but he's telling us about all these electrons. They have these states and so on. So there would be specific energies would be given off. But this is an instrument where you just measure the intensity of the light before and the intensity of the light afterwards. And it's still, you see, this is missing and this is not, went through. And this is how these line spectra look like. So this one would, there's an absorption spectrum. This is the absorbance here, and this is the energy. So what would that be? The wavelengths would become longer or shorter this way? Longer, okay. The frequency would become longer or shorter this way? Higher or lower? Lower, good. So this, if you have this spectrum here, what kind of light would you see? Orange, a little bit of orange, but mostly here. There's nothing here, see? You would see blue here in this case. A little bit of orange maybe, but mostly orange, okay? Now we know this light absorption is the promotion of electrons from a lower state to a higher state. So if the electrons are in a higher state, they have to give it off again. So they give off the same energy than they were excited to. From that level, they go back to the ground state. And with this, you have this would be a line spectrum here. Now we have, okay, this would be the emission spectrum. You see, that's the emission spectrum. So what would that emit mostly here? So this has, what has it absorbed here mostly? Green. And what would emit? That's the emission spectrum, the opposite. It goes down now to 0, also green. If it absorbs, it has to emit it again. Now the line spectrum we understand now because it's concrete levels. Okay, n equals 1, 2, 3, 4, 5, 6. So it absorbs certain wavelengths out of the visible spectrum. And then they're gone. Right? You see black. There's no, you don't see the color anymore. And of course, if you absorb this, you also have a line emission spectrum. Goes from discrete levels of your electronic states to other discrete levels of your electronic states, or to the ground level. So this would look like this then here. What it had absorbed first, now it's emitting. And I showed you a mercury vapor lamp. Mercury, we heated it up, and we brought it in electronic excited states, and it comes down and gives this white light. Very bright white light. People in the front here, they were blinded. Where is he? He's sitting here. You were sitting here. You were blinded there. Yeah? Okay? And so I put something in front of it. It was this white light, but we dissected it. We ran it through a grating, and then I showed you, actually, there was 1, 2, 3 lines that was made different colors that make this white light. There was a fourth one in the UV, so that's even very dangerous. Not very dangerous, but you get UV radiation in your eyes. Okay? So wear sunglasses the next time to come to the lecture. All right, so I'm going to step on it here. So we had this de Broglie relation. We had the de Broglie relation that unified the dualism between light as a wave and light as a particle. So we had this let me see where I was here. Did I? Yeah, I did that, okay? So we go backwards here. I got to breathe. I've tried to push through here. High energy, that's me, okay? Light can also behave as a particle. We have established that light is a wave, but it also can behave as a particle. And the smallest unit of light as a particle is called what? A photon. And light comes in quantum, in packages, a package of smallest units of energy, photons, okay? And so we have, it can be have a wavelength, and it can have if it's a particle, then it has momentum. Momentum is mass times velocity, and we know the wavelengths here, and here we know the momentum. Now we have to marry this. The wavelength is h divided by the momentum, so I can calculate the momentum from a wavelength, and I can calculate a wavelength from a momentum, all right? So this is the dualism between, and this is de Broglie who unified this. Then light can ionize things. It has transfer energy. You have seen, Greg has shown you the ones in the morning, they even got a demonstration. The ones in the afternoon didn't get it. But he had a metal piece, and that piece of metal, metal has nuclei and electron, okay? And the nucleus hangs on to the electron. And if this is the nucleus and this is the electron out here, has an energy between it, binds it, okay? That's the binding, and we know now what that energy is. That's that level energy, okay? It binds it. So in order to rip it off, that metal, that it gets ejected in a much more scientific language, it gets ejected from the metal, I have to put energy in there, and that energy has to be larger than that binding energy, okay? And that binding energy for each metal is different. And we call this the work function. I have to put that work in there that work that I have to put in there, or the energy that I have to put in there, has to be at least as large as the binding energy of that electron. So I have to put in actually a little bit more in there. So you can shine light on a metal surface and nothing will happen because it's not the right energy. But if you have the right energy, then the electron will be dislodged, and the rest of the energy, because you have this binding energy that you have to overcome, but your light had a certain amount of energy which is larger, the rest of the energy would be impaired imparted, not impaired, imparted as kinetic energy of that electron. Now, if you have the same metal and you have light with higher energy than the one which just dislodged that electron, so you would dislodge that electron and you would have higher kinetic energy of that electron, because the rest goes into kinetic energy, and this was shown to you that red did nothing. It's too long of a wavelength. The green did it, gives the kinetic energy. Then the blue did it even more kinetic energy. You need only a certain energy to get it out of the metal. And this is the kinetic energy. So for example, this was the green frequency here. Can you believe this? I just fixed this. Was the nu zero, this is called. And so the kinetic energy is h times nu. H times nu is that energy here minus the work function, and that means h times nu minus h times nu. So that's the initial energy that you need. That's the extra energy that you get here. And this work function is different for different metals. If you look at this, for example, here, this would be metal 1, and metal 2. So if I have a light, a wave, a photon with this energy, that would be the kinetic energy of this here on metal 2, and then metal 1, it would be much higher kinetic energy. You see that? All right. So lecture 5, we know that electrons can behave like particles, but they also can behave like waves. So now we know that electrons are particles, but I have shown to you that they behave like waves because they also have an interference pattern. So there we have the dualism again. Like we had it with the light, we had it with electrons. They can be particles and waves, and the last 3 lectures, we talked nothing about else but waves, and we talked about the electron to see what kind of energy states that can have, and how do these wave functions look in 3 dimensions, S, P, D, F, okay? This is all it is. It's the wave function, the solution to the wave function. So they can form interference pattern, and you've seen that, and I need 3 hands. So you can use, of course, the de Broglie relation for this particle-wave relationship. Particle-wave, same thing, de Broglie relationship. So, and we have seen that the electrons, I did this in a 1-dimensional case, they behave like standing waves, and the lowest number is n equals 1, that you can have a standing wave. That means a half a wavelength in a 1-dimensional case. And so that means the energy of level 1, whatever it is not 0. It has an energy. You can calculate it with the Bohr's equation. So there we are with our standing waves. The electrons behave as standing waves, and the energy is quantized. And you see here, we have the ground state, n equals 1. That's the energy is the ground state. How many nodes? 0. We have n equals 2. How many nodes? So there is 1 node, okay? N equals 3. How many nodes? Okay, alrighty. And so state 1 is the lowest, and these are now our main quantum number. Is our main quantum number. So you see now that now this starts by itself. I don't know. This is PowerPoint, obviously. I don't know why it does this, but it's good. I don't have to do it. You see that there are certain wavelengths fit, certain wavelengths don't fit. All right. And so this didn't fit because the spacing wasn't there. E equals h times nu. And we can do the emission spectrum. We go from the highest to the lowest, and you get these, let's go back here, you get these 3. So what would be the lowest emission that would be possible? It's not shown here. What would be level 1, 2, 3, 4? What would that be? 4, 2, 3, okay? That's the lowest energy that can be emitted in the system. And now you know that the de Broglie wavelengths, you can calculate the de Broglie wavelengths for anything you want. It has to make sense. You can't calculate it for a truck or a football or a soccer ball or whatever. It has to be within the dimension or an order of magnitude of the dimension of what you're trying to describe. So only small particles are quantum particles. We have talked about this. And so wait. Okay. You know the uncertainty principle? I explained it to you. You don't need to know the Schrödinger equation. And this is what we started. So this is the equation that we need. What is that called in the book? The Bohr equation. Isn't that right? Called the Bohr equation, okay? So you have this here. Now, use your iClicker. Was this review useful? Very, somewhat, no, not at all. I don't really need a review, okay? 1, 2, 3, or 4, A, B, C, or D. I have to start too? Oh my God. Okay, there you go. I see you on Monday.